Download this code from codegive.com, link in the description below. OK, let's dive into a robust 5-step process for tackling coding problems, complete with examples to illustrate each step. This approach is designed to make problem solving more systematic and less daunting, regardless of your skill level. The 5-step coding problem solving process. 1. Understand the problem, clarify and define the most crucial step. 2. Plan your solution, design and outline before you write a single line of code. 3. Implement the solution, write the code, the translation of your plan. 4. Test your solution, verify and debug, essential for correctness. 5. Optimize and reflect, improve and learn for efficiency and future growth. Let's explore each step in detail, with concrete examples. Step 1. Understand the problem, clarify and define. This is where you make sure you fully grasp what's being asked. Rushing into coding without a solid understanding is a recipe for wasted time and frustration. Read the problem statement carefully, multiple times, don't skim. Pay attention to every detail. Identify inputs and outputs. What information are you given, and what result are you expected to produce? Define constraints and edge cases. Are there limitations on the input size? What happens if the input is invalid or empty? Ask clarifying questions, if possible. If you're working with a real-world problem or in a collaborative setting, don't hesitate to seek clarification. Example problem. Given an array of integers, find the maximum sum of a contiguous subarray, containing at least one number. 1.1 Breaking down the problem. What is a contiguous subarray? A sequence of elements that are adjacent in the original array. Example in 1, 2, 3, 4, 5, 2, 3, 4 is contiguous, but 1, 3, 5 is not. What is the maximum sum? The largest possible sum you can get by adding up the numbers in any contiguous subarray. What if all the numbers are negative? The problem specifies containing at least one number, so the answer would be the largest negative number. Input an array of integers, example -2, 1, -3, 4, -1, 2, 1, -5, 4. Output an integer representing the maximum sum, example 6 from the subarray 4, -1, 2, 1. 1.2 Edge cases empty array, what should we return? Typically, an error, 0, or a specific value is returned depending on the context. Array with a single element, the maximum sum is simply that element. Array with all negative elements, return the largest negative element. Key questions to ask yourself. Do I fully understand what the problem is asking? Can I explain the problem to someone else in simple terms? Have I identified all the constraints and edge cases? Can I work through a few examples by hand to understand the desired output? Step 2. Plan your solution, design and outline. Now that you understand the problem, it's time to devise a solution before coding. This involves choosing a data structure, if necessary. What data structure is best suited to store and manipulate the data? Selecting an algorithm, or approach, what sequence of steps will solve the problem? Consider different algorithmic paradigms, example brute force, divide and conquer, dynamic programming. Writing pseudocode or a high-level outline. Break down the algorithm into smaller, manageable steps. This helps you structure your thoughts and catch logical errors before you write code. 2.1 Planning for the maximum subarray problem. Approach Cadane's algorithm, A dynamic programming approach is an efficient way to solve this problem. Idea iterate through the array, keeping track of two variables. Current_max, the maximum sum ending at the current position. Global_max, the overall maximum sum found so far. Pseudocode 2.2 Explanation of the pseudocode. The pseudocode outlines the core logic. 1. We initialize global_max to a very small value, -infinity, to ensure that any valid subarray sum will be greater. 2. We iterate through the array, element by element. 3. For each element, we update current_max. We have two choices, either start a new subarray with the current element, number, or extend the existing subarray by adding the current element, current_max plus number. We choose the option that yields the larger sum. 4. We update global_max by comparing it to the updated current_max. 5. After iterating through the entire array, global_max will hold the maximum subarray sum. Step 3. Implement the solution, write the code. Now, translate your pseudocode or outline into actual code. Focus on clarity and readability. Write clean, well-documented code. Use meaningful variable names and comments to explain your logic. Break down the problem into smaller functions, if appropriate. This makes the code more modular and easier to debug. Follow coding style conventions. Consistency in formatting, indentation, and naming conventions makes code more maintainable. 3.1 Implementation in Python. 3.2 Explanation of the code. Def max_subarray_sum, ARR*, defines the function that takes an array ARR as input. Global_max equals float, INF, initializes global_max to -infinity, ensuring that the first positive sum, or the largest negative sum if all elements are negative, will replace it. Current_max equals 0 *, initializes current_max to 0. This represents the maximum sum ending at the current position. For number in ARR*, iterates through each number in the input array. Current_max equals max, number, current_max plus number, This is the core logic of Catane's algorithm. It updates current_max by choosing the larger of two options. Number, start a new subarray at the current number. This is necessary if the previous current_max was negative, as adding it to the current number would only decrease the sum. Current_max plus number, extend the existing subarray by adding the current number. Global_max equals max, global_max, current_max, updates global_max by comparing it to the updated current_max. This ensures that global_max always holds the overall maximum sum found so far. Return global_max returns the maximum subarray sum. Step 4, test your solution, verify and debug. Testing is absolutely critical. Don't assume your code works just because it compiles. Create test cases. Include a variety of test cases, including basic test cases, simple inputs that you can easily verify. Edge cases, empty arrays, arrays with single elements, arrays with all negative numbers, arrays with very large numbers, etc. Stress tests, large inputs to check for performance issues. Run your code with the test cases and check the output. Does it match the expected output? Debug your code using a debugger or print statements. If the output is incorrect, use debugging tools to step through your code and identify the source of the error. Write unit tests. If appropriate, for larger projects, consider writing automated unit tests to ensure that your code remains correct as you make changes. 4.1 Testing the maximum subarray solution. 4.2 Debugging tips *****. Print statements *** strategically place print statements to display the values of variables at different points in your code. This helps you understand the flow of execution and identify where errors are occurring. **Debugger **Use a debugger, available in most IDEs, to step through your code line by line, inspect variables, and set breakpoints. **Rubber duck debugging Explain your code to a rubber duck, or any inanimate object. The act of explaining the logic can often help you identify errors. Step 5, Optimize and reflect, improve and learn. After your solution works correctly, take some time to optimize it and reflect on the process. Analyze the time and space complexity of your solution. Can you improve its efficiency? Consider alternative solutions. Are there other algorithms or approaches that could be used to solve the problem? Refactor your code for readability and maintainability. Can you simplify the code or make it more modular? Learn from your mistakes. What did you learn from this problem? What could you have done differently? Document your solution and the lessons you learned. This will help you in the future when you encounter similar problems. 5.1 Optimization for maximum subarray. Cadane's algorithm is already very efficient. O(n) time complexity and O(1) space complexity. There's not much room for significant optimization in terms of time complexity for this specific problem. However, you can always consider code clarity make sure variable names are descriptive and that the code is well commented. This helps with maintainability. 5.2 Reflection What did I learn about Cadane's algorithm, how does it work, and why is it so efficient? What types of test cases did I need to consider? Did I miss any important edge cases? Could I have solved this problem using a different approach? What aspects of my code could be improved? Example, string reversal. Let's apply the 5-step process to a simpler problem, reversing a string. 1. Understand the problem input a string, example hello. Output the reverse string, example all. Edge cases empty string, single character string. 2. Plan your solution approach convert the string to a list of characters. Use 2 pointers, one at the beginning and one at the end of the list. Swap the characters at the 2 pointers. Move the pointers towards the middle until they meet. Join the list of characters back into a string. Pseudocode 3. Implement the solution, Python. 4. Test your solution 5. Optimize and reflect time complexity O(n), where n is the length of the string. Space complexity O(n), due to converting the string to a list, in Python. In some languages, strings are mutable, and you could reverse the string in place without creating a new list, resulting in O(1) space complexity. Alternative solutions some languages have built-in string reversal functions. You could also use recursion, but it's generally less efficient for this problem. Key takeaways understanding is paramount spend ample time understanding the problem before coding. Plan before you code design a solution on paper or in pseudocode first. Test thoroughly. Create a comprehensive set of test cases. Optimize and reflect. Always look for ways to improve your solution and learn from your mistakes. Practice regularly. The more you practice, the more natural this process will become. By following this structured approach, you'll become a more efficient and effective problem solver in your coding endeavors. Good luck.